Good morning, everyone. Today I will present the findings and recommendations for the rehabilitation strategy of the 9.5-kilometer corridor between Nobi Connection Road and Road 80. This work forms part of Assignment 3 and builds on earlier analysis. The presentation will cover the existing condition of the road, the investigations carried out, structural and design assessments, cost evaluations, and the integrated strategy we recommend to ensure safety, durability, and value for money. This presentation has been structured to follow a logical flow. I will begin with an introduction outlining the background and objectives of the project. Then I will move into data analysis, where I will present the information collected and how it has been assessed. Following this, I will discuss the preliminary designs, including both granular and asphalt overlay alternatives. I will then present the economic evaluation and whole-of-life costs, which compares these options in terms of performance and cost effectiveness. After that, I will highlight additional data requirements and comments on the adopted intervention criteria. Before moving into the integrated strategy that outlines immediate, medium-term, and long-term actions. Finally, I will close with the conclusion. This structure ensures a clear step-by-step approach, linking the technical analysis with practical recommendations. This project focuses on a 9.5-kilometer corridor that connects regional traffic between Toowoomba and Warwick. The primary purpose of this work is to assess the pavement's current condition and provide recommendations for both preservation and renewal treatments. The corridor is a critical link for freight and local traffic, and its performance directly impacts road safety and transport efficiency. By carefully evaluating the condition and structural capacity, we can propose treatments that extend the service life and improve user experience. The first step in the assessment was a visual inspection of the corridor. This allowed us to identify surface defects such as flashing, rutting, patching, and bleeding. These observations gave an early indication of where the pavement was under stress and helped to validate later data analysis. In addition to visual inspection, two key datasets were available. The first was the serviceability dataset collected by TMR in 2022, which included International Roughness Index, skid resistance measured by SCREAM, and surface texture expressed as mean profile depth. The second dataset came from deflector graph testing in 2025, which provided deflection bow measurements to assess structural capacity. Together, these three sources, visual inspection, serviceability data, and deflection data, provide a comprehensive picture of the pavement's performance. The International Roughness Index was plotted against chainage along the corridor. A threshold of 4.2 was applied, which represents an acceptable ride quality. Several sections exceeded this threshold, particularly around areas of patching and rutting. Poor ride quality affects driver comfort, increases vehicle operation costs, and accelerates deterioration in other pavement layers. The results clearly demonstrate the sections of the corridor have already reached an unsatisfactory level of performance from a user perspective and require intervention. Skid resistance, represented as SFC50, was compared against a threshold of 0.30. In many locations, values fell below this limit, indicating compromised skid resistance. In addition, macrotexture, measured as mean profile depth, fell below 0.70 millimeters in flashing areas. These two parameters combined indicate significant safety concerns. Low skid resistance is associated with higher crash risk, especially in wet weather, while inadequate texture. Visual inspection confirmed the data results. Common defects observed included flashing and bleeding in sprayed seal areas, rutting in wheel pads, patching where local failures had been repaired, and general surface leveling. These defects are typical of pavements approaching the end of their serviceable life. They reduce safety, lower ride quality, and allow water ingress that accelerates structural damage. These photos illustrate the visible impacts of the performance indicators already discussed. In addition to the serviceability survey, structural testing was undertaken using the deflector graph. This provided deflection ball parameters across the corridor, and in some areas results exceeded tolerable limits. These values highlight where the payment structure is insufficient. At this stage, our assessment is largely based on this deflector graph data. However, the scope of investigations was limited and more detailed testing will be required before a final design can be adopted. For now, these findings point to the need for structural strengthening. The corridor is founded on vertosol soils, which are expansive and moisture sensitive. These soils exhibit low CBR values, often below the 15% required by MRTS-05 for subbase layers. The corridor also passes through areas that function as floodways, meaning drainage is a critical weakness. Inadequate drainage allows moisture to infiltrate the subgrade, further weakening the pavement and causing differential movements. These geotechnical and hydrological issues must be considered alongside structural design to avoid premature failures. A simplified profile of the existing pavement shows a sprayed seal over granular base and subbase, underlain by weak subgrade soils. Analysis of deflector graph data revealed that several sections exceed allowable deflection thresholds, confirming that the pavement lacks sufficient structural capacity. The lower subbase material does not comply with MRTS-05 requirements for strength, further compounding the problem. These findings indicate the structural strengthening is necessary in addition to surface treatments. Granular overlays were evaluated as one of the key rehabilitation options for this corridor, which required thicknesses ranging from about 110 to 200 millimeters, depending on the chainage and existing pavement condition. The primary advantage of granular overlay is their relatively low upfront cost and the availability of local materials, which makes them attractive for budget-constrained projects and sections with lighter traffic. However, granular overlays are highly dependent on drainage performance, and moisture conditions. Without effective drainage, the risk of premature failure increases significantly. They also require thicker layers to achieve structural strength compared with asphalt, which can create constructability challenges during placement and compaction, particularly under live traffic conditions. But these charts limited over granular overlay with 200 millimeter thickness. Some sections should be suggested reconstruction because of above 200 over granular. Asphalt overlays typically designed at a thickness of 130 to 150 millimeters using dense graded asphalt, class 320, represent a strong long-term solution for this corridor. As the same reason, like overlay granular, above 150 millimeter asphalt sections should be considered full reconstruction as a solution. They provide both structural and functional benefits. Structurally, they strengthen the pavement to carry heavier traffic, and functionally, they immediately improve ride quality and skid resistance. One key advantage is that asphalt requires less thickness compared with granular overlays, which makes it easier to construct under live traffic conditions and reduces user disruption. In our analysis, overlay thicknesses were determined using empirical design charts, which provide a useful initial guide. However, these solutions are preliminary, and before adopting final overlay designs, additional field and laboratory testing must be undertaken. With DCB testing, test pits, and laboratory characterization, a mechanistic design approach will be possible, giving us more confidence in fatigue and rutting performance predictions and ensuring the overlaying design is fully optimized. When we place granular and asphalt overlays side by side, the differences become quite clear. Granular overlays provide a lower cost entry point with material typically available locally and relatively straightforward construction. They are an attractive option for lighter traffic sections or where budgets are very tight. However, they rely heavily on good drainage and moisture control. Without this, they are prone to early deterioration, and the thicker layers required to achieve strength can be difficult to construct under light traffic conditions. Over time, their higher maintenance needs raise the overall cost. Asphalt overlays, on the other hand, come with a higher initial cost, but they deliver significant benefits. Because of their higher stiffness and durability, they provide longer service life, fewer maintenance interventions, and immediate improvements in ride quality and skid resistance. They also achieve structural strength with less thickness, which makes them easier to build under traffic. In assignment 2, we saw that in several sections, granular solutions alone wouldn't meet the structural demands without drainage upgrades, and asphalt overlays were recommended as the more sustainable choice. Ultimately, the comparison shows that while both treatments have a role, asphalt is the stronger long-term option for critical sections, while granular overlays can still be justified in less demanding parts of the corridor. The key message is that treatment selections should be section-specific, balancing cost, performance, and site conditions. It's important to emphasize that the design options I have presented are preliminary and cannot be considered final. To confirm the appropriate solutions, further investigations are mandatory. Dynamic penetrometer testing should be undertaken across representative sections to measure in-situ subgrade strength in more detail. In addition, test bits should be excavated to visually inspect layer thickness, collect samples, and identify any variability in the pavement structure. Laboratory testing of these samples is required to determine material properties, check compliance with MRTS 05 specifications, and assess moisture sensitivity. These combined investigations will provide the robust data needed to finalize overlay thicknesses and validate mechanistic design inputs. In addition, falling weight deflection tests should be is required to carry out back analysis for existing materials if stabilization process required. In this section, we looked at the options not only in terms of initial construction cost, but also from a whole of life perspective. That means we considered the upfront costs together with the long-term maintenance, periodic rehabilitation, and how much value each option would provide over the design period. For example, in assignment 2, we saw that while the granular overlay option may appear cheaper at the start, it's likely to require earlier interventions and more frequent maintenance under heavy traffic conditions. The asphalt overlay option, on the other hand, has a higher initial cost, but offers better long-term performance and fewer interventions. When we assess them through a whole-of-life cost lens, the asphalt solution demonstrates better economic efficiency over time. This method helps ensure that our recommendations are not only cost-effective at construction, but also sustainable, reliable, and financially responsible across the pavement's full design life. One of the primary challenges we face on this project is the lack of adequate drainage solutions. Without proper subsurface and surface drainage, there is a high risk of moisture ingress, which accelerates pavement deterioration and reduces structural capacity. Another critical issue is the presence of expansive soils, which are highly reactive to moisture changes and can cause heaving, cracking, and loss of serviceability. Addressing this requires careful selection of overlay thickness, material stabilization, or even subgrade treatment. Finally, we need to consider construction-related risks, such as traffic management during works, weather sensitivity, and material availability. These factors not only affect the practicality of implementing the selected alternative, but also the long-term performance of the pavement. Together, these challenges highlight the need for robust design decisions that integrate geotechnical, drainage, and constructability considerations. In the immediate term, thin asphalt resurfacing is recommended for sections with critical safety risk due to the low skid resistance or poor texture. These quick interventions will restore safety and serviceability for road users. Immediate works should also include sealing cracks and preventing further water ingress. These short-term measures are essential to maintain functionality while more substantial works are planned. In the medium term, targeted overlays are required to restore structural capacity. Granular overlays should be applied in lighter trafficked areas where budgets are constrained, while asphalt overlays should be prioritized for high traffic or structural weak sections. This targeted approach ensures that resources are used efficiently, addressing the most critical needs while keeping overall project's costs manageable. In the long term, more fundamental improvements are necessary. These include upgrading drainage systems to reduce floodway risk, stabilizing subgrade soils to address expansive behavior, and maintaining a consistent monitoring program using IRI, scream, and deflection testing. These measures will build resilience into the corridor, ensuring it can provide reliable service well beyond the next 20 years. The long-term strategy aligns with sustainable asset management principles. In conclusion, the integrated assessment has provided a clear picture of the corridor's needs. Serviceability and safety issues must be addressed immediately through resurfacing. Structural deficiencies require medium-term overlays tailored by section. Long-term resilience depends on drainage upgrades and subgrade stabilization. By adopting a section-specific strategy, resources are optimized, safety is maintained, and payment life is extended. This approach ensures that both road users and asset managers benefits from the investment. Thank you for your time and attention. I appreciate the opportunity to present my work, and I'm happy to take any questions you may have.